Alright guys, welcome back to a new video. So in today's video, I'm going to be talking to you guys about GANs. Now, GANs are Generative Adversarial Networks, and they're one of the most common generative AI models used today. They're used to generate deepfakes of videos, images, or even voices. Now, in this tutorial, I'm going to take you through a full overview of GANs. We're first going to be talking about what they are, how they work, and the architecture of GANs. Then I'm actually going to take you into the math behind how the models work. And finally, we're going to be coding out everything about a GAN from scratch, and we're actually going to be creating our own GAN. This will be a really informative tutorial, so let's jump right into it. Alright guys, so we already know that generative adversarial networks are used to create deepfakes or generated images, voices, and videos. Now let's talk about why they're actually called GANs and the architecture behind them. So essentially, a generative adversarial network, or GAN, is an unsupervised model, but in the unsupervised model, we have two supervised learning models that work together. Now, these two models are called our generator, gen for short, and discriminator. Now, essentially how it GAN works is our generator is going to first generate a latent vector, which is basically you can think of as a random vector. We're going to take the example of trying to generate an image of a dog. So basically, what we want to do is be able to take images of dogs, right? And be able to create new images of dogs from that. So essentially, we're going to have two different CNNs that are going to allow us to do this. Now, a CNN, you can think of it as just your normal or whatever you think of when you think of a supervised learning model. So I have a video on that, but let's think of our discriminators CNN as a multi-layered perceptron, right? And basically, what a perceptron is it's like one neuron in a multi-layered perceptron. So it's one perceptron, right? And what you think of is it would be something like this. So you might have seen this diagram before, but it's basically a bunch of perceptrons connected, right, with our layers and our hidden layers to give an output. Right now, it's called a multi-layered perceptron because each one of these different nodes is a perceptron. Right now, what our CNN is going to do is it's going to basically, for our discriminator, be trained on a bunch of images of dogs, and it's supposed to be able to predict, given an image of a dog, if it's a dog or not. Right now, so we're going to give our discriminator, we're going to give it images of dogs, and what it's going to do is be able to predict dog or not. All right, now our generator is going to be able to generate data. So first it's just going to generate a random latent vector, right? We can just put random numbers, and these are going to be the parameters that are going to be associated later with our dog, right? And what it's going to do is it's going to give this latent vector, and it's going to give it to our discriminator. Now, our discriminator is first, before this process even starts, it's going to be trained on our images of dogs. And it should be able to be accurate in predicting if it's a dog or not. So what the discriminator is going to do is it's going to take this image, and it's hopefully going to predict, okay, it's not a dog. Because remember, this is just a latent vector. So what's going to happen is it's going to say the results of both of the answers. So the generator thinks that it's a right answer, but it's wrong. So it's going to say false for this one. But for the discriminator, it got the right answer. So it's true. Now, essentially what's happening is you can kind of think of the models competing against each other. So the goal is you want to be correct, right? So the end goal of this entire thing is the generator should be able to fool the discriminator. So now after we get this result, right? Let's say that the discriminator is true, right? And the generator is false. So the generator came in thinking it was true, but the correct answer was it's false. It isn't a dog, which the discriminator predicted. So now the generator has to update its model. So it's going to take the loss, right, of our loss function, which is used to calculate the loss between the correct answer and the answer that we gave, right? So the correct answer for a dog that it has. So just in simple terms, let's say a dog has four legs, right? It's whatever height, and essentially the parameters of this generator could be the height as 10 feet, the like no fur, right? So the generator's parameters is completely wrong. And now you have to be able to change these parameters so it can generate an actual dog later on in the future. So now the generator is going to take our loss function, and in GANs we use cross entropy loss, right? Or in this case, we're going to be using binary cross entropy loss, right? It's also known as log loss. And this loss function is going to give us a loss so we can use that number to change our parameters. So then we'll have a more accurate representation of a dog, right? So right now it's just going to be, you can almost imagine it as just a random image, right? Just latent vectors. And now we're going to change it a little bit based on our loss. You can almost think of maybe we can like add a head, right? So our parameters are going to keep changing, and this is just a simple example, right? And eventually, the generator is going to be able to fool the discriminator. So, so it's going to generate such a good image of a dog that the discriminator thinks it's a real dog. Now, remember, these are just random vectors that have been changed with our loss, and now we've actually been able to create a dog. So now the generator is actually true because uh, it fooled the discriminator, and the discriminator is false. Now, what this means is we have to update our discriminator model because it can't be fooled by a fake image of a dog, right? Now, the discriminator model can be updated, and these models are going to be working together. Eventually, we're going to have a generated image of a dog. So now let's talk about our log loss because that's really important. In other tutorials, I talked to you guys about CNNs, so I'm not going to go too over how that works. I'll give you a simple overview after I explain the log loss, but now let's talk about the log loss. Now, the reason why we're using binary log loss or binary cross entropy is because we only have two different things. Is it a dog or is it not? Now, we can think of these two different things as 0 and 1. So basically, we can use these in the future, right? Now I'm going to talk to you guys about the math behind log loss. All right, guys. So this is the equation for log loss, and it may look like a really long equation, and you might not understand it at the first thought, but I'm going to explain it step by step. So, first, to understand this equation, we need to understand the two different variables that you need to solve this equation. So we have y and we have w. Now, y is what is the actual output that your model got. So, for example, this in this binary cross entropy is either going to be 0 or 1. Those are the two values that y can be. Now, 0 meaning not a dog in this example, and 1 meaning it is a dog. All right. Now, the W is going to be the weighted sum. And I'm going to talk to you guys about that by explaining to you guys the actual architecture of a perceptron neural network. So that's what I said when I was going to explain CNNs. So essentially, in a perceptron network, we have different inputs, right? Now, this is almost a similar structure to a multi-perceptron network. But it's a little bit different. So we have inputs, and connected to these inputs are what we call weights. Now, the weights are what actually are going to change. So you can think of our weights like almost our parameters. Now, our inputs don't change. So these could be like the different pixels of a dot. Now, our weights are going to change. Right now, it's just a latent vector, so it's pretty random. These are going to be passed to an activation function. Now, we're going to be using the sigmoid activation function later in this video, and I'm going to explain to you right now why that's a great activation function for our use case. So, a really common activation function is the ReLU activation function. Now, the difference between the ReLU activation function and the sigmoid activation function is that the sigmoid activation function is going to help us with our outputs of a number between 0 and 1, right? As the equation is 1 over something, right? And now what that's going to do is going to make our output to a number between 0 and 1. Now, the only two outputs that we have are 0 and 1. So that's why the sigmoid activation function is really useful, right? So we're gonna say sigmoid activation function. And I'll explain that a little bit more when we go into the coding part. But essentially, after these inputs and weights, we pass them through the sigmoid activation function. We're going to calculate the loss, and then we're going to bring it right back, change the weights, and then repeat this process so we have an accurate representation, and we can give a proper output, right? Now, basically, the weighted sum is just going to be all of your inputs, right? We can just put random values. Now, it's going to be your inputs times your weights. And you're going to get the sum of them. So it would be, we'll say, we'll call them I1 times W1 plus I2 times W2, and then so on, right? That's going to be your weighted sum. And what that's going to do is it's going to basically allow us to get a number that we can say, is it greater than 0.5 or is it less than 0.5? And that's going to be our predicted output. So if it's greater than 0.5, we're going to say, okay, it is a dog. And if it's less than 0.5, we're going to say, okay, it's not a dog, right? And that's where we get our y value. Now, the y value is what your actual, what the actual output is, okay? So essentially the y value is, okay, we have our output with our weights, but what is the actual output that we should have gotten? So now we can calculate the loss, right? So now that we know the two different variables that go into this function, and you get those from our generator, we can look at this actual equation. So you can think of this first part of the equation as a for loop. So in coding, what we do is, so first we can ignore this first part, but essentially what this sigma means is we're going to loop for every single number in n. Now our n is just going to be all of the different inputs that we have. So essentially what we're going to be doing is we're going to go through every single input, find the loss, and then get the average of that, right? And the average is we're going to be multiplying it by 1 over n. And that's essentially dividing it by the number of inputs that we have. So we're going to go for I in n. We're going to do this equation, right? So we're going to calculate that equation, and then we're going to get the average of that by multiplying it by -1 over n. Now, as you'll see when we code out this part, most of the, or actually all of the answers to this equation, after you plug it in, they're all going to be negative. So that's why we're multiplying by negative 1 over n, so we can just make it a positive output. So we can actually ignore this part right now, so we can focus on what is the loss for one input. Now, let's imagine that for the first latent vector, the actual output was 0. Our generator obviously thought it was 1, so we're going to have a W, a weighted sum, of let's say 0.9. Now, what this means is if the weighted sum is 0.9, it means it's greater than 0.5, which the model thought it was a dog, but the actual answer was it wasn't a dog. Now, if you think about this, there's really only one part to this equation that you can actually solve. It's either log of W or it's log of 1 minus W. Sorry about that. So basically, if y is 0, then this entire part is canceled out because 0 times anything is 0, so it doesn't really matter. And if y is 1, then this part of the equation is canceled out because 1 minus 1 is 0, right? So essentially, we're either doing log W or log 1 minus W, right? Now, log W. So we're going to be doing, right, in this case, y is 0, right? So we're going to be doing log 1 minus W. Or that's the only thing that we can do because it's 0. So we're going to be doing log of 0.1. Now, the log of 0.1 is, all right, well, the log of 0.1, which again is 1 minus 0.9, well, this is negative 1. Now, this is an accurate representation as our model isn't going to be this far off, right? It's not going to be the total opposite, as it thinks 90% sure that it's a dog, even though it's not, right? Now, that's why we have this big of a jump, right? It needs to do a full 360 because we're thinking the opposite, right? It's not a dog, and we're thinking almost 100% sure that it's a dog. And remember, this number can't be 1, right? So now you can see that this is negative. So that is why we had the negative 1 over n in front of our equation, right? So that's going to turn into just 1. So now let's say that our model actually got it right. So it is 1, and which is greater than 0.5, right? So it did get it right. So this is what we actually want in our model. Well, the loss of this is way less. It's so the log base 10 of 0.9 is actually only 0.045 or 6, right? So 0.046. Now, this is perfect. Well, this is what this is showing us is the model knows that it is correct, and just to get a little bit closer, you just want to change by this much, right? So now we know how binary cross entropy works, and the math behind it. Now we know this equation that really is big, we can actually write in probably less than 5 lines of code. So let's start coding it. So this can be the code for our binary cross entropy, and as you see, it's really simple. So I said 5 lines of code, 1, 2, 3, 4, 5, and the rest is just printing out, right? So basically, first we're just going to import math. Now, all this is from scratch. It's a really simple formula when you think about it. And all math is doing is it's just a built-in Python module. It's just going to help us with the logs, right? So all we're doing is we have our data. And remember, these are our variables y and w, right? So y is going to be the y hat, the actual output. And then we're going to have our weighted sum as w. So, right, so this is the weighted sum. And then this is the y hat. Now, remember, we don't need the actual y, which is the input's corresponding output, right? What it thinks the answer is, because that's just going to be, is it less than 0.5 or greater than 0.5, right? Now, as you can see, we just have a list of all these different inputs, right, of weights and y hats, and we're just going to set our loss equal to 0. Then we're going to loop through every single I in our data, so every single one of these tuples, and that's literally what the equation was, right? So you saw sigma and it was looping through every single input in our end variable, right? Now, then what we're going to be doing is we're going to get the I loss. And what that is that's just our equation. So this is essentially y hat, right, which is this, right, 1, times the log of our weighted sum plus 1 minus our y hat times the log of 1 minus our weighted sum, right? That's really simple. And then what we're going to be doing is we're going to be adding it to our loss variable. Finally, we're going to be dividing it by the number of numbers, right? That's what we did with 1 over n in the equation. And then finally, we're going to be multiplying it by -1. And as you'll see, you'll notice that every single one of the outputs is a negative number. So that's why we have to multiply it by -1. So we can run this module and you'll see the different logs and then we'll see the average of the loss, right? Now let's go back to our data. So understand that 3 of these data is completely wrong. We have 0.74 and 0, which this is saying that the model thinks it's 74% chance that it actually is a dog, but it isn't. And it thinks a 90% chance, which is what I showed you on the whiteboard, but it also isn't. And finally, even worse, is 98% chance that it is, but it is. So that's like on the total other end of the equation. Like we want to have 98% accuracy. Now we're having only 2% accuracy, right? So think about that. Actually, 1 because we can't actually get 100%. And now 30, that's more accurate than the others. At least that's actually predicting the right value, right? So you can see that we got outputs as 0.85. For this, you can see the loss was less, but for the other ones, it's a lot more. Now, one thing I didn't mention on the whiteboard is that's why we use binary cross entropy loss for GANs, right? The reason is because it has a greater loss for incorrect answers. As you see here, it's only 0.15 for the incorrect answer, but you can go all the way to uh 0. Sorry, 1.69, right? So it's on the total other end, and we want these bigger gaps compared to other loss functions that I'm going to talk about right after this section that have smaller increments for wrong answers. Now, the reason why we want a bigger loss if we have an incorrect output is because to generate these new images, we have to be able to change so many different parameters. And for generative AI, this is really useful. So now let's talk about another common loss function. All right, so now I'm going to show you guys the other most common loss function, which is called mean squared error loss. So this is going to actually be used in our GANs, but I just want to show you guys if we used it, what's going to happen while we use binary cross entropy loss compared to mean squared error loss, which is another really common loss function, but it's used for regression tasks. So essentially, it's a really simple equation. It's the same starting, so we're just going to loop through every single input and then we're going to find the average, but instead it's just going to be y minus y hat squared. So it's not going to really help for this case because it's a binary problem. So it's the answer is always going to be 1, right? It's either going to be 1 minus 0 or 0 minus 1. But in this case, we're going to be using the weighted sum instead of the actual output that is being given, right? So it's the same thing. We can loop through every single data point. Sorry. And then we're going to create our I loss, right? And we're just going to set this equal to I0, right, minus I1. And then all of this is going to be squared, right? So we can square this. And then we can add this loss to our loss, right? So plus equals. And then we can find the average by printing total loss, right, plus, and then we're going to do our loss divided by length of our data, right? So it's just finding the average. And let's print this out. Let's also just print out each loss so we know. All right. So now let's run this. and we get our losses. So as you can see, the loss of our binary cross entropy, right? And now this isn't the perfect example because it is a binary. So when you get into more complex GANs where where you can create multiple images or even videos and sound, it's going to get way more complicated. In this case, we just want to create an image of a dog, right? And basically you can see that it's not actually making that much of a loss for the compared to the binary cross entropy. You can see here it's 1.6, right, or almost 1.7, and here it's only 0.96. It's still big, but it's not as big as the loss as the binary cross entropy, right? So that's just a quick example about why we use binary cross entropy loss. This is going to be the GAN code, and it's just going to be running on this fashion MNIST dataset, which is a super popular dataset created by TensorFlow. I'll put the link in the description down for that. But essentially, I'm going to show you guys the main parts about this code, and then I'm just going to put it on GitHub. So first, we're just going to load this dataset. I'll show you what that looks like in a little bit. And then we're just going to be creating our generator, right? And these are just the layers for the generator. Just to mention, I'm not going to go too deep into the code. As I said, I'm just going to show you an overview. And maybe in another video, I'll actually code this out with you. But we're going to create a generator, and then we're going to pass a latent vector into the generator, right? So what that's going to do is it's going to give us a starting place, so then we can do our actual GAN process, right? The generative adversarial network, right? Adversarial meaning we have two different models that are working against each other, right? To get better outputs, right? So the generator passes to the discriminator, and it's kind of like a game that they're playing for who can get the right answer, right? So that's why it's called adversarial. And basically, then what we're going to do is we're going to create a discriminator, which is just also a bunch of layers, right? But it's using the sigmoid activation function. Remember, discriminator is itself a model that can identify the images, right? So it's supposed to be able to identify fashion or not. So that's why we have the activation of sigmoid, right? So so then what we're going to do is we're going to predict based on the image that was generated by the generator, and in our actual model class, we're going to find the loss between the actual answer, right, and the generated image. As you can see over here, we have right here, we have the loss, so total discriminator loss, and we're just going to be using self dot d loss, which is just our binary cross entropy. And we're going to get that loss, and we're going to go through a training loop with 20 different epochs. Right now, it's still running. It's been running for about 10 minutes, and it's only on the 7th epoch. And basically, it's just going to take that loss. It's going to go back and use back propagation, right? And what back propagation is we're going back. We're going to update our parameters, right? And then we're going to pass it back through forward propagation, which is passing it through our activation function, and then obviously doing the process that we showed on the board for GANs, right? So that's what our function is doing, and it's just going to do it 20 times, right? So now I want to show you, just in the epochs it's done already, 8 different epochs now, how the GANs have actually worked, so how the process works. So we start off with this a latent vector, right? As you can see right here, it's just blank space, right? It's just a blank white image. And now let's see how, as we go through our epochs, how the image changes. So we're still in the first epoch, and you can see nothing has changed. But now as we go to the first epoch, you can see it's taken the loss, right? And it's changed, right? So it's changed into this image over here that's kind of starting to look more like an actual image, right? And as we keep going through the epochs, let's go to 5, you can see it's kind of trying to form some type of fashion, right? So maybe this is going to be like a shirt or something like that. So now we can look at the last one. We have this type of image right here. Now you won't know how the process worked until the end, so let's just wait until all of the epochs are finished. Alright guys, so that's it for today's video. Hope you guys enjoyed. If you have any questions about the tutorial or any concepts I mentioned, you can put them in the comments down below. And as I showed, the results weren't looking like the actual fashion in the dataset, which is fine as we only ran it for 9 epochs. I was using the free version of Google Colab, and that only had a CPU. You can run all this code on your computer if you have a GPU, or even if you have the paid version of Google Colab, it'll run a lot faster. So for optimal results, you want to run the code up to at least a couple hundred times, maybe even about 2,000. So once you hit about 2,000, you'll see the data start to look like the actual data set. Anyways, that's it for today's video. Hope you guys enjoyed. And until next time.